Hello and welcome back to Organic Chem Chapter 11, Spectroscopy. This is the second to last of the chapters for Organic Chem as well as almost the end of the series. So we have infrared molecular vibration as our first topic here. A wave number, don't be confused with a wavelength, is actually 1 over the wavelength. So it is actually in frequency. It's just another connotation for frequency, the wave number, and its measurement in cm, the inverse or the 1 over cm. And basically, it is when you shoot infrared at some molecular compounds and they start vibration. So if I put molecular compound here, the bonds start vibrating and they absorb that energy to vibrate, right? But you need to have a dipole or a difference in electronegativity for this to happen. If there's O2 compound, then since there's no dipole present, there won't be any change in vibration, right? Because they're just reorient themselves because they have the same electronegativity. So there are few bonds to know the absorption spectrum for. Hydroxyl OH has a broad peak at 3300 cm-1, and that is alcohol. For the 3000, it's carboxylic acid, and broad peak, as shown here. This is measurement in percent transmittance versus wave number. So around the 3300, it's going to have a big broad peak over here for hydroxyl group, the OH bond. That bond's going to vibrate at that corresponding frequency. And remember, the higher the wave number, the higher the frequency, right? Because that's basically the same thing, different from wavelength. So OH has basically a short wavelength. That's how it corresponds to a higher wave number. So as it vibrates, that's alcohol, and carboxylic acid, if it will move down over here, but still remain a broad peak. Now, because it's percent transmittance, the lower the transmittance, the higher the absorbance. That's how it's in shape like a dip instead of an upward curve. NH has a sharp peak around 3300, so it will be about here, but it's like a sharp little crevice. Carbonyl group, C double bond to O, will have a sharp peak at 1700. So way down there, 1700, and have a nice sharp peak. The way I remember these three is OH has a nice broad O all around, because O is pretty big and round. NH, because I think N has like the sharp ends, right? That makes it sharp. And CO has a sharp end because this looks like an arrow, right? The point C pointing towards that way. Ultraviolet is like the next part. If we want to measure the ultraviolet absorbance, it's a little different because we have to look at how the double bonds in the pi systems correspond to it. We don't have to remember any numbers, but just know that ultraviolet is useful to look at pi bonds and basically on hybridized p orbitals. By following the orbital molecular theory, this is the highest orbital with highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. The closer they are to energy, the closer the gap, the more they're able to hybridize and form new orbitals, right? We've seen sp2 is hybridizing 1s and 2p orbitals, right? And we've seen how they're able to hybridize into conjugated systems. Those respond to ultraviolet waves to resonate. There's no numbers to memorize here. Just need to know that they can excite the molecules that can conjugate bond with each other. So those are the ones that have remember the Hans rule, right? For 4n plus 2. All right. Then we have nuclear magnetic resonance, NMR imaging. Basically, it's the fundamental way of how MRI works. You basically shoot the protons and see how well they're shielded or deshielded from the magnetic field being sent in. Right? MRI is magnetic resonance imaging, and the gray parts is where the water are present, and the light part is where fat are present. So to look at this graph, we see the parts per million in delta. The more left, it's more deshielded, because if we look at this molecule here, the protons here, H, has bonded to a central carbon that's bonded to 2 more electronegative atoms, and they draw, because they're electronegative, they draw the electrons away from the center and from the hydrogen itself. With less electron density, it becomes less capable to shield itself from the magnetic field coming in at it, so it gets pushed around and more deshielded towards the left side. If for these 3 hydrogen atoms here, since there's no electronegative atoms near here, nothing to deshield, it still retains those electron densities and is able to shield itself from the coming magnetic field. And since there are 3 of them, they stack up higher and higher up here. So the integration here, if you integrate this area, it should be 3-to-1, because there's 3 of these hydrogens over here. TMS is basically just the marker which we base it off of. We don't really need to care about it. That's basically 0. Alright, and if we were to substitute the Cl for something that donates electron density, like carbons, right, then it would be likely an electron donated, so it will be right shielded instead. Alright, that's basically it.